All right, hello and welcome. This is Stats 101C, Statistical Models and Data Modeling. And I believe we have stuff posted on Brew and Learn. Let me see what it looks like as a student. And so basically in this course, I wrote, welcome to summer session. My vision for the class is that we are going to cover machine learning stuff, and then we are going to focus on application. And so I have these kind of big group projects planned, and that's going to be the bulk of your course grade. And my hope is that these projects will be challenging, but also a good opportunity to learn and understand how to do statistical modeling. There's a lot that I want to cover. Unfortunately, I don't think we'll be able to fit everything that we have within those 6 weeks. But I want to spend a lot of time kind of just on the practical nuts and bolts of how do you set up a workflow, and the tools that we're going to use, tidy models. There's a debate on whether the class should be taught with Python or whatnot. We're not going to use Python because one, not all of you have taken Stats 21 or have Python experience. And number two is tidy models is a great package. It's a great kind of system and framework that we can use to do statistical modeling. A lot of the pieces that exist in tidy models also exist in machine learning packages in Python like sklearn. Tidy models calls certain things like recipes, but basically you're setting up a pipeline or what tidy models calls a workflow, where you'll do feature engineering aspects, some resampling, some recipes, and you'll build up your models that way. And a lot of those elements also exist in Python packages like sklearn. And so what you learn in tidy models, if you choose to use Python and sklearn in the future, a lot of those concepts will translate over. Of course, the commands and exactly what you need to write and how you do it will be different, but a lot of the concepts will carry over. So I don't think learning tidy models is a bad thing or anything that you're going to be losing time on. Let me go back a few slides. So we are going to be covering quite a bit of kind of machine learning stuff and its applications. And one thing I really want to point out is that these 6 weeks will go by very quickly. Just in a couple weeks, you're going to really want to start getting started on your projects. There's going to be 2 projects. One's going to be a regression project and one's going to be a classification project. You're going to want to establish your groups within, I would say, by the end of the first week. So then you can start thinking about and start working on those projects. Just move and keep up with all of this stuff. Okay, the textbooks that we will be using is one is Introduction to Statistical Learning. Let me open that. And the other is Tidy Modeling with R. Both of these are free to read or download. So you can download Introduction to Statistical Learning. And this one is ISL with R, and this is ISL with Applications in Python. This is actually pretty much the same book as this. The illustrations and whatnot are still made in R. It's just kind of the homework exercises and the labs are done in Python. But other than that, they're pretty much the same textbook. Tidy Modeling with R is going to help us work through kind of a system called tidy models. So this is like an extension of the tidyverse. So in R, you have the tidyverse kind of created by Hadley Wickham, and author of dplyr and ggplot and tidyr and tibble and all of these kinds of things, and Tidy Models works with the Tidyverse and sets up the kind of a framework for doing statistical modeling. And this was authored by Max Kuhn. Max Kuhn is kind of this I don't know, legendary machine learning author, and so this is also an excellent resource, and you can read the entire textbook for free in your browser. If you want to purchase and pay money to get the paper version, you can do that, but the browser version, as far as just reading all of this in here, it's all of the same content. So it's pretty great. Okay, and then the other thing that we'll spend a lot of time reading will be the documentation for Tidy Models, and there's quite a bit to cover as far as the Tidy Models documentation. That's just at tidymodels.org. Okay. Okay, so I will have, I guess, in the homework, I have the kind of first homework assignment posted. I'm going to assign exercises and problems from the textbook. I think they are some pretty good exercises, a good mix of kind of challenging and doable. And you know what? Because they're coming from the textbook, you can find solutions to these exercises. They exist on the internet. But I strongly encourage you not to look up those solutions, okay? And to work through them yourself. Because the whole point of me assigning homework is that this is an opportunity for you to kind of learn and develop your skills. I don't actually care about, as far as these homework exercises go, I don't actually care about the answer itself, okay? You will get, as far as grading goes, you need to have the right answer to get full credit, but the whole point of me assigning the homework is for you to learn from it. And so please view the homework as a learning opportunity. The analogy I always like to use is going to the gym. And when you go to the gym and you're lifting weights, the point of lifting weights isn't so that we have weights picked up off the ground. Okay, that's not the point. The point is that the process of lifting the weights is going to make you stronger. All right, and if you are lifting only weights that are easy for you to lift up, you can't expect to get stronger from doing that, okay? You need to do things that are challenging to you. And so my hope is that the homework assignments and the group projects, that they will be a challenge to you and will be a good opportunity for you to kind of try these things out and develop your skills, okay? So, your brain develops and learns when it goes through that struggle. And so when you do struggle, resist the temptation to look up the answers and instead, struggle through it and force your brain to learn and create new connections and pathways as you work through it. Okay? Before I get into the content for the first stuff, let me point out a couple things on the class website. One of these things is this teammate finder and group sign up page. You have to be signed into Google Apps. So let me do that. And I think it's right here. So I filled out a couple things, but basically I've copied the roster from the class website, or I guess from my UCLA here. I've copied all of your names, and I want you guys to fill this out and use this and reach out to, as you see students fill this out, reach out to them and say, hey, do you want to form a team? Okay. I put in a few things here, whether you found a group, okay? And if you do find a group, fill that out in team info. I've got, teams 1 through team 20 or whatever, and you'll just put your names in here. That's fine. Okay. You can put in your contact information, kind of how many hours per week you're willing to contribute towards the project, and then basically your availability to meet on Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. And that way you can start, try to find teammates that have compatible schedules. Some of you, with this being an online course, some of you might be on the other side of the world. And so, you might try to find teammates who are in similar time zones so that you have compatible times to meet. So put in your availability here. I put down, there's a spot where you can write down things that you are good at and things that you're not so good at, so that you can try to find teammates that complement your strengths and weaknesses, so that, different aspects can be done. And then also kind of any kind of additional information that you might want to put on here, right? So you can say, I really want to get an A on the project, and I'm willing to work hard, and I want other people who are also going to work hard for it, or something like that. Okay. Or, you can also just kind of be honest in terms of like what else you have going on in life. So some of you might be working an internship, and so that's something that you shouldn't hide from your teammates. And if it's kind of like, well, I'm going to have limited availability because during the week I'm going to be working, but I'm willing to put in the hours on the weekend and stuff like that. Put that in there, and that way you can find kind of teammates who are going to be compatible, and so just so kind of the expectations are clear up front. I know group projects can be frustrating. I've certainly been in my share of frustrating group projects, and I find kind of the most what causes a lot of conflict in group projects is different expectations regarding like how much effort and what we're willing to put in. And so the best projects are when everybody's kind of on the same page and says, hey, all of us really want to work hard and we want to do that. Okay. If everyone's kind of just like, hey, let's all just kick back and play it easy, that's fine too. All right. But a lot of conflicts arise when you have a mix between some people who are really ambitious and some people who don't really want to put in the work. Those kinds of things can cause stress. And so just I think just put it out there and just kind of say like, hey, this is let's be realistic about this kind of stuff here. Okay. So you can put all that in there, make as much, write as much as you want in this kind of other information for self-statement. And then, once you find or look at, notice there's some classmates of yours that you might want to work with or be compatible with, you can put that in there. Okay. You can also just say like, hey, you know what? I'm already friends with so-and-so, and I want to I already want to work with this person. And we're looking to kind of look for another, 2 or 3 teammates. So the teams, either 4 to 5 people. Okay, 4 to 5 people to a team. That's what we're going for, and so you need to have at least 4, and the max you can have is 5. So, but you do want to start thinking about your teammates, and I'll set up some kind of deadline where if you haven't found your teammates, I'm going to just start throwing people together. Okay. So that probably won't happen until sometime during the second week, but I would say, during this first week, make sure you just at least start filling this information out and start looking for some teammates. Okay. So I would say by the end of the second week, if you haven't found teammates, I'm going to start assigning them to you, but those are always a little bit risky when you get assigned to a group that you really didn't have much control over. Okay. I've posted a syllabus. Let's just take a quick look at that. And then, let's see. Okay, so my syllabus has gotten longer every single quarter. So now it has a table of contents, and it's up to, I guess, 10 pages. Okay, so the lecture format is, I'm recording these videos. I'm going to post them, and you'll watch them. I'm going to have little quizzes that go along with each video that you'll be required to respond to. Okay, I'm going to have office hours multiple times during the week, and that's going to be your best way to get your questions answered. You can email me, but I am a little bit slow at responding to emails, so I would encourage you to come to office hours if you need quick responses. I will send out invitations to CampusWire. You are required to participate on CampusWire to get credit for that. Or actually, no, I'm sorry. I am not requiring CampusWire. I did not put that in the grade. So my apologies. That's the other class. The other class I required CampusWire. This class I'm not requiring CampusWire, but I think it can still be helpful as far as discussion and asking questions of your classmates. Okay. I will give you more information regarding the final projects, but again, they're going to be conducted on Kaggle. Okay, so Kaggle is a website that hosts these data science competitions, and we're going to have two separate competitions. One's going to be a classification project competition, and one's going to be a regression competition where you're going to be predicting values. And I'm still kind of searching for the right data set to use for these things, but my hope is you'll be able to do a good job there. Okay. And then you'll also have some homework assignments. I've also sent invitations out to Data Camp, and just because some of the homework assignments will require Data Camp for you to kind of complete a course and print out your certificate of completion or things like that. So, on Data Camp, you should receive an invitation. Make sure you accept the invitation using the same email address that was invited. So I used the email addresses that are listed on BruinLearn. Some of you have emails that end in @ucla.edu. Some of you have @g.ucla.edu, and others of you are using your personal email addresses like @gmail.com or whatever. Just make sure you use the correct email address, because if you try to create an account using the wrong one, so let's say I invited Joe Bruin @ucla.edu, and then you try to create Joe Bruin @g.ucla.edu, DataCamp doesn't know that you're the same person, and they will not give you access to their premium content. Okay, so DataCamp kind of has this classroom support system, and they give access to their premium content, but I only get a certain number of subscriptions that I'm allowed to give out, and I can't just I can't give two subscriptions away to one student. So make sure you use the email address that was invited. Okay. All right, let's take a look at our first video here. I mean, our first lecture here. Okay, so let's look at this chapter 2 of Introduction to Statistical Learning. So this textbook right here, and you can download it. I think it's downloading right there in the background, but this is kind of the idea. And so the textbook calls it statistical learning, whereas I would say most of the rest of the community calls it machine learning. But I think the the textbook authors, they are statisticians, and I think they still kind of want to claim ownership over, or they want this to be known that this is based in statistics. So they call it statistical learning, but it's most other places they call it machine learning. And so what is that all about? And so they break it down into a few different concepts. And so let's talk about these things. Okay, so before we get into it, let's cover a little bit of notation. And the idea here is, in statistical learning, is you have inputs and you're trying to predict these outputs. Okay, so our input variables are gathered in maybe a big matrix called X. Okay, so we have this big input matrix called X. We have n observations. Each observation is a row, so we're going to have n rows. And then we have p different features, or p different variables. These are the things that we're going to use to make our predictions. And so each of those columns or features or variables, we're going to have p of them. Okay, so if you take your rectangle and you think about each of these columns, we can call that first column x1, and we can call that second column x2, and so on and so forth. Okay, so each column is going to be a vector, and each of those columns will have n observations or n values in them. Okay, so the jth column, xj, is going to be the values, x1j, x2j, x3j, all the way down to xnj. Okay, so each of these things, right? Whereas each row, okay, is an observation, and we're going to we denote the observations. So for the columns, we use kind of bold print X, and for the observations, we use italics X. Okay, so X italic X1 is the row, the first observation. And so each row has P values, P features. Okay, each one's a vector of length P. So we have italics Xi is going to be the ith observation, and we will have xi1, so the ith observation's first variable, xi2, the ith observation second variable, so on and so forth until the p. And so the entire X matrix can be represented as the columns x1, bold print x2, all right, up to bold print xp. Okay, or we can think of it as a bunch of rows where we have row italic x1, so observation 1, observation 2, observation, and transpose. So those are ways you can think about the X matrix. Meanwhile, you have this output variable y. Okay, some books call it t, the target variable, but here we have the output variable y. These are the values associated with each of these things. And we just have one value, so we're not going to do this kind of multivariate thing where we have multiple variables that we're trying to predict, but just one variable that we're trying to predict. So this could be, whatever our response variable is. And so that's going to be just kind of n observations, each of these things being a scalar value there. And we are saying that there's some kind of relationship between that output variable y and the input variables, at least one of the input variables x, okay? And so there is some function that relates the inputs, okay? So for the ith observation, if we were to take the ith observation in x, plug that into some kind of function, and then maybe include some random error, random noise, we would get the output variable, the ith observation in our output variable. And we're saying there's some kind of relationship that actually exists here, okay? So f represents some unknown function, and so the whole idea of statistical learning is that, yeah, there is some kind of function, and we're trying to figure that out, or at least figure out an approximation for it, okay? But there's always going to be some leftover thing that can't be explained, and that's going to be the error term. And we're assuming that error term has a mean of 0, so that overall this function approximates the true relationship to y. Okay, so here is just kind of just a made-up example here. I guess we're trying to say, hey, is there a relationship between the years of education and income? And this, I think, is just some made-up data here. I don't know if the relationship is this strong here. But the idea is, hey, this is what we observe, and perhaps there's some true relationship. And the true relationship is modeled with this blue line. Okay, this is the true relationship that's modeled with this blue line, so that, you know, overall, as the number of years of education goes up, the income also goes up. Perhaps the, you know, once you get past a certain number of years of education, additional years don't really make a huge difference, but perhaps in this area it does make, you know, each additional year of education makes a difference and things like that, a big difference. And so, so this is simulated data. Normally, this blue line is unknown to us, but here we actually know what it is. And the dots that we've observed, these red values, these are kind of the observed values. And here, there's we have a difference between the red dot and what the line predicts. And so these vertical black lines represent kind of the error, or basically, yeah, how different is the actual value from the true relationship. Okay, and the idea is that if you added up all of the kind of the residuals, you know, all of those residuals have a mean of 0. So, you know, why do we bother? Why do we bother trying to estimate this relationship f? Okay, so in essence, this whole concept of statistical learning, machine learning, is how we are going to try to estimate this function. And the real goals that we have are trying to make better predictions, okay, or try to learn something, try to do some inference about the relationship between x and y. And really, depending on which of these goals, the prediction or the inference, is more important, will influence, you know, the choice of model or approach that you're going to use. So, yeah, okay. So in a lot of these situations, the input values, the inputs in x are readily available, but the output y isn't as readily available. And so with the assumption that the errors average to 0, we can predict y using y hat by just kind of plugging in x into f. So our f hat represents our estimate of the true relationship to f. So a lot of times we don't know what the true relationship is. We have to estimate that. And once we have kind of the function that we can use, we plug in our x values, and we're going to get predictions, and that's going to be y hat. Okay, this function f hat, sometimes we can treat it like a black box, meaning we don't actually care what happens on the inside of it. We just want to be able to put in values, and if it spits out good predictions, we don't actually care what's happening inside the box. Okay, how is it doing it? We don't really care. Okay, and that's kind of where we are with, say, like neural networks or you know, these large language models like ChatGPT and things like that. Those are really, really, really complicated systems. It's really just a function, but with billions of kind of parameters that are estimated, and we don't really know or fully understand what's happening inside a large language model. It's been trained, and we can see, like, okay, if we put in this prompt or this question, this is the output that it gets, and we look at that output and we say, hey, that's pretty good, and we're happy with that. But as if if you were to ask, hey, how is it doing that? How does it know what to say? It's people don't really understand. Okay, a lot of these things, like how does TikTok recommend, know what videos to put in your feed, or YouTube or whatever. We know that they perform well in that people stay engaged. People, the next video that shows up, people interact or engaged with it. And so we know they perform well, but how does it work? It's a little bit of a mystery. And so when people say, hey, we need to tweak the algorithm so that it doesn't promote these kind of bad videos or things like that, it's not so easy. It's not so easy. All we can do is just try to give it some feedback that says, hey, when you do promote this video, you're penalized for it, and maybe it will learn. But it's a little bit like, how does your brain work, right? When you hear something, and like when you try to learn something for an exam, it's not that you actually know which cells and neurons in your brain are connecting to each other, but we can kind of evaluate whether you've learned something by giving you a prompt and asking, can you create the right answer? Can you give the correct response? And if you are able to, we say, oh yeah, you must have learned it, okay? And if you're not able to, we say, oh, you haven't really learned it. But it's not like we're going to open up your skull and look at your brain and say, oh yeah, we see these neurons connected to each other, and therefore we know the person's learned it, okay? So these are situations where we just treat what's actually happening in the brain or in the neural network or whatever as a mystery, and we evaluate how well it's working by just the performance of the predictions, okay? How the just in general, the accuracy of y hat as a prediction of y depends on kind of two different parts, okay? One is what we call reducible error. That is the difference between our model that we've estimated, the f hat, and the actual relationship f, okay? So we're saying there's some actual relationship f between x and y, and we want to approximate that. We approximate that with our model f hat, and the closer and closer f hat is to the actual f, that we've reduced the reducible error, okay? So that error can be reduced, and it's minimized when f hat and f are exactly the same. On the other hand, the irreducible error, this epsilon part, okay, is cannot be reduced in that even if you knew the exact true relationship, there's still going to be leftover kind of quote error. So you might know the true relationship between x and y, but in life there's random effects, things that affect the outcome at random, and so even if you know the true relationship, because of just randomness and stuff, there's going to be some leftover error, and that part cannot be reduced beyond a certain point, okay? Or it just can't be reduced, right? And so you can have two observations that have the same x values, but they produce different output values, okay? So this is irreducible because no matter how well we estimate f, we're still not going to be able to get rid of the error introduced by epsilon. So this is summarized, okay, in kind of our bias variance trade-off. So we say, hey, what's the difference between y and y hat? Okay, the expected value as far as the difference between y and y hat. Well, we can kind of break this apart, and we can say we've got the difference between y is going to be f of x and epsilon, and then y hat is going to be f prime, or f hat of x, okay? And we can kind of take the difference here. That's going to be the reducible component, whereas the epsilon, that's the irreducible component. So that's kind of the idea of estimating f as far as as far as predictions go. The other kind of motivation we have for estimating f is for inference. That is, we're trying to kind of understand the relationship that exists between x and y. So sure, making predictions, that's always desirable. But in some cases, having good interpretability might be more important than the predictions, okay? Being able to understand what is happening, how do you explain the relationship between x and y? That might be the more important aspect, okay? And so, questions that we might have that we want to answer are things like, which predictors are associated with the response? What's the relationship between the response and each predictor? Or, even something like, what is the form of the relationship? Can we explain it with a linear relationship? Do we need something more complicated? These are the kinds of questions that we might want to answer. And so in that case, we're going to model f with the goal of inference in mind. How do we go about estimating f? All right, so just in kind of a general sense, we might have this training data where we have our inputs x and our y. And so here, this italic x, remember, is not necessarily just one scalar value, but it's actually a vector, a p-length vector. Okay, so this is the entire vector of predictors. And we have n of these observations. So we have, our input vector x for the first observation, and then the actual y value for the first observation. Then we have it for the second observation, and so on and so forth. All right. And what we want to do is we want to apply some kind of statistical learning method, all right, to this data here. We call this the training data because we're going to use it to train our model and figure out, figure out some kind of function f hat that we're going to then use. Okay, so we want to find this estimate of the function where we can plug in x and get a predicted value. As far as what kind of methods exist, broadly speaking, we have parametric and non-parametric methods. Okay, parametric methods say that estimating that function f is a matter of estimating a set of parameters. There's kind of, two parts for parametric methods. One is we make an assumption about the functional form of f. So, for example, we might say the functional form of f is a linear model with these parameters. So we can say, we have some coefficient for the intercept, some coefficient times basically the coefficient for the x1 variable, a coefficient for the x2 variable. And we have different coefficients for all of these things. Your model could be more complicated. You could have quadratic terms and things like that. But basically, you're making some kind of assumption about what is the form of this relationship between f and y. Okay, and so once you've made an assumption about the form, then what we have to do now is we just got to figure out, okay, what are the values that we should use for our coefficients, beta 0, beta 1, beta whatever, right? And so we have to estimate these parameters. And so, you learned all of this in 101A when you did regression, okay? We take the training data to train the model. As far as linear regression goes, you try to find the parameters that will minimize the sum of squared residuals and things like that. You minimize your kind of squared error function. And that's going to estimate your parameters. And that's how we approach kind of this parametric, the parametric problem or parametric method is we make some kind of functional assumption about the form of the function, and then we then go ahead and estimate the parameters. So this parametric approach simplifies the problem by turning it into just estimating parameters. Okay, usually estimating a few parameters is a lot easier to do than estimating some arbitrary function that could be very complicated or something. Okay, but the problems can arise is that when you make the assumption about the functional form, if that doesn't truly match the true relationship to f, then you're going to run into problems. And so when you learn linear regression, one of the big assumptions is that your errors are normally distributed and you have homogeneous variance as far as the residuals go. And you check to see if the resulting residuals after you fit the model fit those assumptions, because if they don't, then perhaps your model assumptions are wrong, right? So that's going to be important, is that you kind of want to verify and double check that the form that you are assuming is mostly correct. Okay, you can kind of avoid issues of fitting the wrong model by fitting a very flexible model. So you can fit in a whole bunch of terms and parameters, and you can just keep making your model more and more complicated. Okay, and these highly flexible models will have lots of parameters that you'll need to estimate. So you might want to fit like a fourth order polynomial function for each of your terms or something, and that will allow for your model to be very flexible. But that could also lead to overfitting, and we'll talk about that. But overfitting is basically the problem that arises when your model ends up fitting the noise that exists in the data. So there's always kind of this leftover noise that's not actually part of the true relationship, but because you've estimated a model that's so flexible, it ends up fitting that noise, because in your random data set, certain bits of noise could appear. So that could happen. Okay. The other approach is the non-parametric approach. So the parametric methods make assumptions about the functional form. Non-parametric methods do not. They do not make assumptions about the functional form. And so non-parametric methods can fit a whole bunch of different possible shapes. For f, it doesn't require that the function f fits a certain shape or anything like that. Okay, and so when you use a non-parametric model, you're not going to ever run into the problem of using the wrong parametric model. You're never going to run into the problem of saying like, uh-oh, we thought it was linear and it wasn't linear. Okay, that's only going to happen if you assume things are linear. But if you say, hey, I'm not going to make any assumptions about the shape, then you won't run into that problem. Okay, the issue with non-parametric methods is that they generally require a lot of data to get any kind of accuracy. Okay, so usually you need a lot more data just to kind of arrive at the same kind of predictive performance. So here's an example. This is, again, some fictional data, and the idea was they're trying to model what is the relationship to income. If we're trying to predict how much money does someone make at the job, it might be related to how many years of education that this person has, also to how much seniority they have at the workplace. So seniority meaning like they just started would be low seniority, and they've been working there for 30 years will be high seniority, okay, and how much education they have. And so the idea here is this blue surface represents the true relationship between years of education, seniority, and income. And so we see if you have few years of education and low seniority, you'll have lower income. More seniority and more education, you'll have higher income. And there's some kind of relationship. It's not a flat relationship, but there's some curvature to it. Okay, and that's how it goes. There's also some, and these red dots represent individuals, and there's going to be some some leftover error. And so you have some red dots. So this person, their income is lower than what the true relationship indicates it should be. This red dot is higher, meaning this person's making more money than what the true relationship should be. And then that's, down to, kind of just personal differences and things like that, luck and stuff. Things happen where some people might be higher or lower than what the true relationship is. And statistical modeling or statistical learning is all about trying to estimate what this true relationship, what this blue surface might look like. Okay, so one approach is to use a simple model. This uses a linear model. A linear model in three-dimensional space means just a flat plane. Okay, this only needs a couple parameters to fully specify this thing. Okay, and so what we see is that the relationship between income and years of education is a straight line. The relationship between income and seniority is also a straight line. Whereas, in real life, there's kind of some curvature. So we lose that when you use this thing, okay? But it's simple to estimate a linear model because there's only a couple parameters to figure out, okay? But again, rather inflexible model, only able to kind of fit this flat surface, and so we miss out on kind of the curvature that exists, okay? Over here, this is a spline model, okay, non-parametric thin plate spline model, covered in one of the later chapters. They specified that the splines should try to fit a smooth surface, and so it tries to do that, okay? Makes no assumptions about what the relationship should be, tries to fit smooth surface to these things, tries to shrink down some of the errors. There's still a little bit of error. You can see some of these dots are below or above the surface. And if you compare it, and then we go back a couple slides to the blue surface, we see it does a fairly good job, but looking at this line here for the relationship between seniority and income, it's not exactly the same, but overall, we'd say it does a pretty good job, okay? This one is another thin plate spline model, and here, when we specified the model, we said, hey, you know what? Don't worry about it being smooth. Just really minimize the errors as much as possible. The surface should fit the data as closely to possible. And so when you look at this, now there's like no error because the surface goes through every red dot perfectly, okay? But now we have kind of this bumpy surface, okay? This bumpy surface in that, this is saying that as seniority increases, your income's going to go up and then go back down and then go back up again, okay? As your years of education increases, it goes up and then down and up and down and up. And that's not really how the true relationship works, right? The true relationship says as years of education goes, it increases and then it keeps going up, but not as rapidly. Same kind of thing with seniority. It's in the beginning, seniority doesn't really matter. At a certain point, it starts to matter more and it increases, and maybe at another point, seniority doesn't really matter. But here, when you fit this, you kind of have this roller coaster thing where it goes up and down and things like that. And this means we've overfit the data. The red dots, we fit them really, really well, but we fit it a little too well. And we're saying, because in our data, what we saw was that here's an individual who I don't know, has, let's say, 12 years of education and makes, more money, and this person has more education, maybe 14 years of education, but they make less money. And so we said, oh, because that exists in our data, we're going to say when you have 12 years of education, it goes up. When you have 14 years of education, it goes back down. And that's not really how it goes. That happens to be true for these individuals. But if you look at like everybody, the true relationship should be that the person with 14 years of education should have more income than the person with 12 years of education. And it's just that this individual with more education, just for what other reasons, not part of our model, perhaps makes less money. Maybe this person just has a difficult personality to work with or something, and that's why that's holding them back. I don't know. Okay, but that's not part of our model. But however, because we said fit the data as closely as possible, it ends up fitting that kind of relationship. And so, we're faced with this overall, there's a few different kind of things going on. One is we don't want to overfit. Okay, we want to find good relationships. We don't want to have models that are too simple either. Okay, there's another part that we want to think about is, what's the trade-off between prediction accuracy and model interpretability? Okay. And you might want to ask, is there ever a point where we want to use a very simple model like this? Okay. Why would we ever want to have this kind of restrictive model instead of one that's very flexible? Okay. Well, if we are interested in inference most of the time, where we're trying to understand and interpret things, restrictive models are easier to interpret, they're easier to understand, easier to explain. Okay, it's kind of like, what's the true relationship? So if you think, a common thing I hear is like 1 human year is 7 dog years. Okay, and that is a very, very easy thing for people to understand. Okay, so when you say something like, oh, okay, you have a dog that's 8 years old, that's like 56 in human years. Okay, that's a very easy thing. The truth is that dogs do not mature and age at the same rate that humans do, right? They go from a child to an adult in about 2 years. Okay, and then they age a little bit slower than that. But it's a lot harder to kind of explain, this non-linear relationship in simple terms, right? And so if you're interested in something like inference, then just having a very simple explanation, like one human year is 7 dog years, that's a lot easier versus like, oh, as far as like aging, trying to predict your dog's age, you have to consider like, the first couple years it ages differently. And then also, the size of the dog plays a different role, right? Older, heavier dogs basically age a little bit faster. Smaller dogs don't age as quickly. And this is, now things get a lot more complicated, okay? But yeah, if you're trying to go for some kind of simple thing, use an easier model. More restrictive models are also going to not overfit your data, basically. All right, so if you look back to this linear model here, yeah, this is not going to overfit your data. Okay, you actually have the opposite problem, right? And then if you have a highly flexible model, something like this, okay, then to get a truly accurate thing, we would need lots and lots and lots of data, okay? If you wanted a really accurate thing, you need lots of data, where just you don't have this situation where one individual who had 12 years of education brings up the thing, and one individual who had 14 years of education brings it down. But you'd have multiple people with 12 years of education, multiple people with 14 years of education, and you'd see overall the relationship is smoother. So these highly flexible models often require a lot of data to get something accurate. So we have a few different model types that we can use. Things that have high interpretability but low flexibility, that would be things like linear regression. So linear least squares regression, subset selection, that's basically just reducing how many variables you're using as some subset of the variables you're using. Lasso is a technique for selecting some of the variables that you're going to use. So these don't have a ton of flexibility, but they're easy to interpret, okay? On the opposite end, where you have really high flexibility, you have neural networks. These have become very, very, very powerful models as far as making predictions go. And if you have tons of data, which is basically what all of these things are doing, is that they're just trying to gobble up as much data as possible. And now they're making really good predictions, okay? High flexibility, interpretability, nobody has any idea what's happening inside a neural network. All we're doing is we're saying we've absorbed a ton of data and now we can make good predictions, okay? Not as extreme, but still kind of high flexibility, lower interpretability. Support vector machines can do that. We also have boosting trees and bagging also have these high flexibility there. Okay, just a simple tree is something in between, and then you have these generalized additive models. Is kind of like an expansion of least squares regression, but you add splines and kind of flexible fits in there. That's going to increase your flexibility, but you're not going to lose as much interpretability there either. So you get something in between, happy mediums there. We're in this class, we're not really going to get into unsupervised learning, but it's good to kind of talk about this. Is that another way to think about statistical learning methods is to divide them into supervised versus unsupervised methods. In supervised learning, you have the predictors and the responses, and you're able to evaluate how good your predictions are because you know the answers. So in your training data, you say, hey, these are my inputs, these are the outputs, try to predict these things, and you can, and you know the answers, and so you can evaluate this, right? It's kind of like when you take a test and we want to know, hey, did you learn the stuff? Okay. You can take the test, you can write down the answers, and you can say, hey, I'm doing pretty well, right? It would be like the professor releases a practice exam along with the answer key. Okay, so you can take the practice exam, and then you look at the answer key and you say, hey, I got these right, and I got this one wrong, or whatever, right? I got 98% on the practice exam, so I feel like I've done a pretty good job. Okay. Unsupervised learning would be something like a different class. The professor gives a practice exam, but no answer key, and you don't really know. you go through the practice exam and you have answers, but you don't know if your answers are right or wrong. Okay, and so now you don't have a way to tell, hey, did I do a good job? Did I do a good job? Right? So unsupervised learning, you don't have the answers, and you're trying to look for basically structure and patterns in the data. So things like clustering and dimension reduction techniques, you don't have the answers or something like that. So you don't quite know if it's not as easy to know if you're doing better or worse in your performance. So that's unsupervised learning. You don't have the answers, so you can't always kind of compare and see if things are getting better and if you're learning more. But you are still kind of looking for structure in the data. As far as supervised learning, okay, as far as making predictions and checking your answers to see if you did it right, we can divide those into regression and classification problems. Regression is basically the response that you're trying to predict is a numeric response. So examples of that is predict the price of a house based on different inputs. So you think about these different real estate tech companies like Zillow and Redfin or whatever. You know, they have houses or apartments or whatever, living places, living spaces, and it tries to predict this is how much this dwelling is worth and stuff like that. Okay, and that's based on things like the size of the house and the different aspects, and it's trying to predict that. Okay, another thing is basically trying to predict how much money a customer will spend. So if you're a store like Amazon or Target or something like that, you've got a website based on you're trying to predict how much the customer might spend, or if you run a subscription service like Netflix, you might try to predict, okay, how much can we bump up the cost of the subscription and people will still subscribe, and things like that. Okay, so that's regression. You're trying to predict a number, and basically if your prediction is pretty close, you have little penalty. If your prediction is far away from the actual value, you have higher penalty. So if the true value is 10 and you predict a 9, that's pretty good. Okay, if the true value is 10 and you predict 20, now you're 10 points away. That's pretty bad. Okay, I mean, of course, everything's relative, but certainly the predicting a 9 when the true value is a 10 is a lot better than predicting a 20 when the true value is a 10. Classification, on the other hand, is you predict a categorical variable. So, is this email message spam? Yes or no? Okay, you need to categorize it. Okay, is this person going to default or not pay on the loan? That, if you're a bank and you're going to lend somebody money, the worst thing that can happen to the bank is that the person borrows your money and doesn't return it. Okay. And then now you have to kind of chase that person down with collections or something. And so banks try to avoid that. And so they try to predict whether somebody's going to default on a loan. Okay. And so there's just kind of a yes or no. Did you get it right or did you get it wrong as far as the prediction go? Or if you have, some kind of thing where you have multiple categories, basically, did you get the category prediction correct or is it wrong? So that's a classification problem. All right, let's talk about how do we assess our model accuracy. All right, so in supervised learning, it's really important that we are able to assess how well our model is performing. Okay, so because that's going to guide how we fine-tune our model. Okay, if you can't tell if things are improving or getting worse, there's you have no aim or direction, right? It's kind of like if you are sailing out in the ocean, okay, do you turn your boat to the left or to the right? Well, it matters for navigation. You need to know where you're headed. You need to know what your goal is, and if you're kind of moving in that correct direction or not. And if you can't see anything, right? If you have if you can't see the stars at night, or if you don't see any kind of landmarks on the horizon, then you don't know if you should improve your model or not. Okay, it's kind of just like if you have these different knobs to see if things are getting better or worse, you need to know if things are getting better or worse. And so you need to be able to assess model accuracy. So as far as regression goes, the way we measure accuracy is by using the mean squared error. We look at the difference between the actual value, y, and the predicted value. And we do this for each individual observation. So for each individual observation, we have the actual value, yi, and we subtract off our prediction for that particular observation. And whatever that difference is, we square that difference and we add them up. We add it up across all of the different I observations we have. We divide by n, however many observations we have, and that is the mean squared error. That is the average of the squared differences between the actual value and our prediction. What squaring the errors does is it punishes larger errors more heavily. So by using squared error, we're saying, I would rather make a bunch of small mistakes than having one big mistake. Okay, so if you think about, let's say you have 10 observations, okay? One model gets all 10 observations wrong, but it's wrong by 1 point on each of these things, okay? So let's say an observation is 12 and it predicts 11. An observation is 15 and it predicts 16. It gets all of these wrong by 1 point. So your total squared error, your mean squared error, would be each observation has a difference of 1. You square it, you add them up across all 10. So you have 10 divided by 10. Your mean squared error is 1. Okay. Let's say you have another model. Okay. Same 10 observations, and it predicts 9 of those observations perfectly, but it gets one of those observations wrong, and it's wrong by 10 points. Okay. So one model had 10 observations, all of them were wrong by 1 point. The other model has 10 observations, 9 of them are correct, no error, but one error is wrong by 10 points. When you square that error, 10 squared becomes 100 points, okay? And so you're going to have 0 error for 9 observations. The last one has 10 squared, 100. So you have a total squared error of 100 points divided by 10 observations. Your mean squared error is 10. Okay, so getting 10 wrong by 1 point each gives you a mean squared error of 1. Getting 9 correct but 1 wrong by 10 points gives you a mean squared error of 10. So squaring the errors punishes those larger errors a lot more heavily by squaring it. Okay. When we fit the model to our training data to kind of what we're trying to do is we try to minimize the distance between the actual value and the predicted value, right? We're trying to minimize the difference between the actual value y and our predicted value. And we do that with our training data, okay? But when we do this, we don't want to just have a model that predicts our training data super well, okay? So, you know, if you think about learning a concept for an exam, okay, and let's say the professor releases a practice exam, you don't want to be in a situation where you've basically just memorized all of the problems in the practice exam, and so you know the answers, right? Question number 3, the answer is D. Question number 4, the answer is E, without actually understanding the material. So, because you can, if your measure of performance is just, hey, am I getting the answers on the practice exam correct? You can fool yourself into believing you know it really well by just memorizing A, B, C, D, E, you know, just the answers to the practice exam. So you don't want something where you're just memorizing what you kind of see in your training situation, your practice thing. You want to be able to perform well on problems that you've never seen before, okay? You want to be able to, you want a model that's going to generalize to the real world, not just memorize what happened in the training data, but basically also answer questions or make predictions on data that we haven't seen. And so, so what we do is we have our test data, okay? So we have training data and we have tested data. And so it would be kind of like if you want to know, did you learn the practice I guess the material really well, you could if you had 2 practice exams, you can kind of see how well you've done by kind of using one practice exam to learn, and then if you understand those concepts well, then you can try out the second practice exam, and if you're able to perform well on the second practice exam, then you can feel confident that you've learned the material pretty well, okay? Versus like if you just keep practicing on the training data or the same practice exam over and over again, and you just end up kind of memorizing all of the questions and all of the answers, that's not really learning, right? And so, similarly, if you have a model that performs really well on the training data, it's not necessarily going to be the same, have the same kind of performance on the test data. Okay, we want something that performs basically well for data that we haven't seen yet. There's no guarantee that the method with the smallest mean squared error for the training data is also going to have the smallest mean squared error for the test data. Okay. In general, the more flexible a model is, the lower its training mean squared error is going to be. So if you have this really flexible model, okay, it could probably fit or explain that training data super well, okay? And so, on a side note, we wrote that, more flexible models, things like splines or whatever, can generate kind of a huge range of possible shapes to estimate f as compared to kind of less flexible and more restrictive models like linear regression, okay? But these more restrictive models are generally easier to interpret. There's also a trade-off between flexibility and model interpretability, okay? But, the test mean squared error could end up being, in fact, even higher for a more flexible model than for a simple approach like linear regression. And so I want to kind of illustrate this with a few diagrams here, okay? So these diagrams come straight from the textbook, Introduction to Statistical Learning with R. And what you'll see is on the left, you're going to have a few different lines, okay? One is going to be black. That's going to be the true model. This is the thing that dictates the real relationship between x and y, okay? It is unknown to us. We are trying to estimate that true relationship. We have, there are going to be 3 possible lines that we're going to fit, okay? The orange line, the blue line, and the green line. One is going to be, the orange line is going to be a straight line estimate, least flexible, okay? Then you will have a smoothing spline with medium flexibility and a green line with high flexibility, okay? So this is what we have. Just look at the left graph for now, okay? So the true relationship is this black line, okay? The dots show up, this is the data that we get to observe. Okay, we get to observe the data. We don't actually know what the black line looks like. We don't know what the true relationship looks like. We can fit a few lines, possible models, to this thing. One thing is we can fit a straight line, and we can see the straight line doesn't do a great job on this, okay? We see the dots, and it just tries to fit that, okay? We have this blue line, if you can, in light blue, and it tries to fit the dots as best as it can, but we give it just a little bit of flexibility. And so, because we have, I guess, supervision, we can see that it kind of matches the black line fairly well, but not perfectly, okay? And we also have this green line that performs really well as far as predicting the dots go, okay? But we can see it kind of deviates quite a bit from the black line, okay? But what it's trying to do is it's trying to minimize the amount of error. And so, because just in our data set, we happen to get these kind of dots that deviated quite a bit from the black line. The green line tries to accommodate those things and tries to match these dots up here. Okay. Meanwhile, on the right graph, this is a measure of the mean squared error. Okay. The gray is the training mean squared error. Okay. This is a measure of how much error is there. What's the difference between the yellow line, blue line, and green line for the dots. Okay. And so what we see, the yellow line has the least amount of flexibility, and it kind of has the most amount of mean squared error between, there's kind of a lot of dot error between the dots and the line. Okay. The blue line is has a little bit more flexibility, and it has less error than the yellow line. Okay. And the green line, the green dot here, has the most amount of flexibility, and as far as the error goes, it fits these dots a lot better, and so it has even less error in the training data. Okay. This red line, however, represents the test MSE. Okay, so the test MSE would be if we were to generate another random data set around the black line, we would get a whole nother set of random dots. Okay, and so these are random dots, and so if we generated another random set of dots, we might get some dots that appear down here. Okay, and in that case, dots that appear down here perform poorly compared to the green line, because if I put a dot, say, down here, okay, it's going to be far away from that green line. And so the red line represents kind of how much mean squared error we get for a test set, right? And so for a test set with the orange line, it still performs kind of poorly. We get some more error, not as great performance. With the blue line, okay, this blue dot here says if you get a new random set of data, you're going to get some performance. It's not going to be as good because here it's trying to fit the training data, and so again, the test data is going to be off. But then the green dot actually has the highest or higher test error, and just kind of indicates that it's performing poorly for a new random set of data here. Okay, so we see that as far as the flexibility goes, when for the training data, having a more flexible model, sure, that's going to decrease the amount of error that you have on these observations. But if we get new observations, okay, where something that we haven't seen and we're trying to make predictions, its performance just isn't going to be as good. Isn't going to be as good. And so you get kind of the best performance for the test error, mean squared error for the test data with some kind of in-between amount of flexibility. Okay. And so that's all of this kind of commented out. So the blue line is moderately flexible, does a good job of fitting the training data, and it has the kind of lowest mean squared error of the three models for the test data. Okay, this dotted line, this is the minimum possible mean squared error for the test data. This is represents the kind of the random error that appears around the black line. Okay, and so that is irreducible, and so this is kind of the theoretic lower bound for what the mean squared error can be for test data. So what we see is that as the flexibility goes, we get this U shape. In the beginning, low inflexible models perform poorly. As we increase the flexibility, our test data improves, test error improves, but then as we get too flexible, it starts to perform poorly again. Just another example here, the true relationship is this black line. And there's some curvature to the black line, but we see, it's not drastically different from a linear relationship. And so here, when you fit a straight line the straight line does a fairly decent job. Okay, so for the training data, the blue line, it's kind of hard to see, but just has a little bit of curvature to it, and that performs a little bit better. And then the green line, it's trying to fit this data as closely as possible, and so it it's highly flexible, and it kind of for these dots, it really shrinks the amount of error there. And so with high flexibility, it's really reduced the amount of error that we have on the training data. Okay. However, if we were to generate a new random set of points generated around the black line, the true line, we see it's going to perform poorly. As far as the linear line and the slightly flexible blue line, it's not going to make a huge difference, okay? Just because the true relationship being in black isn't all that different from the linear relationship or the slightly flexible blue line. So yes, we get a little bit more error, but how much more? It's not drastically different. Okay, yes, do we get better performance with the flexible thing? Sure, okay? But at this point, you might say, the linear relationship, it's good enough. It's good enough, and certainly it's easier and it's simpler to explain there. Okay, so the blue line here does have the best mean squared error performance for the test data. Using a linear model provides the advantage of being very easy to explain. So the non-parametric smoothing spline might perform better than the straight line, but the performance gains there are very small. Okay, here we have curvature again. Here the linear model does a really bad job. Okay, so its training MSE is very poor. Okay, the blue line does pretty good, fits this pretty well. And then as far as the green line goes, again, it suffers from being too flexible, and so it fits the training data better than the blue line, but not drastically so. Okay, just because as far as the dots go, they're pretty close to the black line to begin with. So as far as the training data, it does perform better. Okay, but if we generated new data, it's going to get worse performance. Okay, but we can see the straight line really just does the most poorly in this kind of model here. Okay. So these graphs that we showed you kind of illustrate this issue of the bias variance trade-off. Okay, we have kind of competing forces that govern the kind of choice of the learning method and how flexible we might want to do, and that's kind of the battle between bias and variance. Bias refers to the error that is introduced by modeling a real-life problem, okay, that's usually very complicated with kind of a much simpler system, right? So, for example, a linear relationship assumes there's a linear regression assumes there's a linear relationship between x and y, okay? In real life, it's unlikely that it's going to be exactly linear, okay? So there's going to be some bias there, right? If the real thing in real life is more complicated, then we're going to have some difference there. Okay, if you have a method that's kind of more flexible, more complex, it will generally have less bias because it's going to kind of be able to fit these more complicated situations a little bit better. Okay, the variance, however, refers to how much will your estimated line change if you had a different randomly selected training data set. So if we had a different random data set, so in these cases, not these dots, but like a different random generation of points, how much would the fitted lines change? Okay, well, the blue line probably won't change drastically, but the green line, I imagine, would change quite a bit, okay? And so that's going to be variance. So if something is very flexible, you're going to have quite a bit of changing or shifting around for different random data. So highly flexible models will have high variance. And so mathematically, we can kind of show that the difference between the actual value and our predicted line, okay, which is f hat of x0, that kind of the expected mean squared error for test data can be shown as kind of the combination of the variance and the bias plus our irreducible error. Okay, and so basically, if you have greater variance here, okay, that could reduce your bias. Okay, or if you have a greater bias over here, that could reduce your variance. Okay, because if your total test or I guess depending on the model, so you can have a model with high variance and high bias or something, and you'll have a total high expected test MSE, but overall the mean squared error, there's kind of this variance and bias trade-off here. Okay, so I'm going to show you a few different additional slides here, and I'm going to generate different sets of training data based on the same true model. The true model is going to be shown in black, and we're going to fit two models, higher flexibility in green and lower flexibility in blue. So here, this is the true relationship is shown in this black line here, and I've generated some random data in red dots. And here I fit a smoother relationship in blue, and then a highly flexible relationship in green. Okay, and you can see this highly flexible relationship, it kind of wiggles all over the place depending on the kind of the data there. All right, and then so here I'm kind of just generating another random set of red dots. Okay, so the true relationship should look exactly the same. So I have three different things. The true relationship for all three of these things should look exactly the same. The red dots are random each time, and so they change for each of these graphs. And you can see that the light blue line changes a little bit, but only a little bit. Like if you pay attention to this little corner down here, you can see, yes, the light blue line does change a little bit, but not that much, okay? Or if you look at over here, the light blue line does change, but only a little bit. But if you look at that green line, it changes quite a bit, right? This green line here is pretty different from the green line here, pretty different from the green line here, okay? So the true relationship, the black line, doesn't change from graph to graph. The red dots change a lot from graph to graph. The light blue line changes only a little bit from graph to graph, and the green line changes quite a bit from graph to graph, okay? And that kind of illustrates this concept of bias and variance, okay? The blue line has less flexibility, and so when we take different random sets of data, it changes only a little bit. That illustrates the idea of low variance, okay? From one training data set to another training data set, there's low variance, okay? It's not changing drastically even though you're getting different random data. But because the blue line consistently kind of underestimates, right? If you look at this thing, it doesn't quite match the black line very well. It's consistently a little bit too low over here and consistently a little bit too high over there. That's going to be the bias part. It's not, there's a difference between the true relationship and, like, if you averaged all of these blue lines, the light blue lines, there's a difference. There's bias there, okay? Whereas if you averaged all of the green lines, okay, if you averaged all of the green lines, it would probably fit the true relationship, the black line, pretty well. So that would be kind of your low bias, okay? However, you see that that green line changes dramatically from one random data set to another random data set, okay? And so that indicates the high variance. High variance because the green line changes quite a bit from one random data set to another, but you have low bias because if you averaged these green lines, you're going to get something pretty close to the true relationship in the black line, because the green line is really very centered around the black line in each of these things, right? It just kind of, it wiggles a lot, but it's very kind of consistently around the black line, every single one of these things. Okay, so we can say that's going to have low bias there. All right, so that's how we assess model accuracy for regression. Let's talk about how we assess model accuracy for classification. Okay, classification, we measure our error differently. The idea of bias and variance still apply, but now the way we measure accuracy for classification, there's a few ways, but one is just the error rate, classification error rate. How many observations do we predict correctly versus how many did we get incorrect? All right, so this is just an indicator. Is the prediction y hat different from our from the actual value? If they're different, our predictions are different, like if it was red and we predicted blue, then indicator puts down a 1 for the error. Okay, if it was red and we predicted red, we get a 0 errors there. Okay, we just count up how many errors we have, the sum of all of these things, and divide by how many we have. So basically, if there's 100 observations and we made an error 5 times, our error rate is 5%. Okay, because we would have 95 zeros and 5 1s for the times we were wrong. 5 divided by 100, 5% error rate. Okay. So let's look at an example. We have a classification model called k-nearest neighbors. The way k-nearest neighbors works, this is a non-parametric thing, is just that you take a test point. You are going to look for the points that are in your training data. You look for the observation that is most similar to your test point. So here we're assuming we have kind of two-dimensional training data, and we're going to use Euclidean distance. So we're just going to say, hey, the observation that is closest to my test case, that is the observation that is closest to it. And in our training data, our observations have classes. They're either going to be orange or purple or orange or blue or something like that. And we take, whatever the class is of the nearest point, and we're going to say that is going to be the classification of my test point. And that's going to be k equal to 1. You use the 1 closest observation. If you have like k equal to 3, with k equal to 3, you look for the 3 nearest neighbors, okay? The 3 closest observations. Each one of those observations gets a vote for what the classification should be, and whichever class has more votes is going to be the predicted classification of the test point, okay? So here, let me just kind of illustrate this. The circles represent our training data. The circles represent our training data, and so what we do is, I believe this is with k equal to 3, okay? Let's say I took this test point right here. So each of these, this whole grid of little dots represents a different test point, and then the circles represent our training data. So let's say I take the test point right here. I say, what are the 3 nearest neighbors we have? We have these 3 points. These are the 3 closest neighbors to this test point here. The closest one is orange, and then the next closest is this purple and this purple. And so each one gets a vote. We have 2 purples, 1 orange. This test point gets classified as purple. Here is a dot right here, and we look at what are the 3 nearest neighbors to this thing. Okay, the 3 nearest neighbors is this purple dot, this orange dot, or the orange circle and an orange circle. And so out of the 3 here, the 3 nearest neighbors are, we have 2 orange and one purple, and therefore this gets classified as orange. As soon as you kind of cross this boundary over here, let's say I look at this dot right here on this side of the boundary, now the 3 nearest neighbors are going to be the 2 purple, and 1 orange, okay? And therefore, this test case right here is going to get classified as purple because of 3 nearest neighbors here. And so this border is going to be exactly halfway between this orange circle and this purple circle, okay? Because if you're right here, your 3 closest neighbors are going to be this, and then you have a tie between orange and purple. And so if you're a little bit closer on this side of the border, then this is the closer one, and your 3 nearest neighbors are these 3. If you're on this side of the border, okay, then your 3 nearest neighbors are going to be these 3, and so you'll get classified as orange. Okay, and so the coloring, you can kind of look at all of these different things as far as what your 3 nearest neighbors are, okay, and this is how things get classified there, okay. So out here your 3 nearest neighbors are all going to be orange, and so this is orange wins there. Okay, so I had an arbitrary test point in green in this upper kind of right corner, and the 3 nearest neighbors of that one was the 2 orange and 1 blue, and so that gets classified as orange, whereas this one, the 3 nearest neighbors, as this one in the lower left, we have 2 blue and 1 orange, and so that gets classified as orange, or as blue. Okay, here's something more complicated, all right? And this dotted line represents kind of the true boundary, okay? The true boundary is shown in this dotted purple line, okay? Dotted purple line is the true boundary between the blue and the orange territories, okay? But there's randomness, and so sometimes orange ends up on the wrong side of the true relationship, true boundary. Sometimes blue ends up on the wrong side of the true relationship, okay? This is the difference between using k equal to 1 versus k equal to 100. With k equal to 1, you use the 1 nearest neighbor to determine whether something is blue or orange. And so we have this kind of one sole blue dot out here, and because we're looking for the 1 nearest neighbor, it kind of carves out its own little enclave that says, hey, this area I'm claiming for blue, okay, with k equal to 1. Because as far as that goes, this is the closest observation to the test point out here is going to be this blue dot, okay? Similarly, you have these orange dots out here, and so it draws this. And so with k equal to 1, you get this really jagged boundary, okay, shown in this black line. And you have these little enclaves and exclaves and things like that, showing that, yeah, you know what, this is, we would say, high variance, depends very much on the random data that was generated. High variance, low bias when you have k equal to 1, okay? Over here with k equal to 100, we pick a dot and we say, what are the 100 closest observations, okay? And apparently, on this side, out of the 100 closest observations, you're probably going to get something like 51 orange and 49 black, and so this gets colored in as orange. Over here, you probably get 51 blue and 49 orange, and so these get kind of colored orange. Out here, maybe your 100 nearest neighbors are mostly blue. Over here, your 100 nearest neighbors are mostly orange. And so the boundary that gets drawn between blue and orange is this black line, which doesn't really approximate the true relationship, again, shown in this dotted purple line very well. Okay, so with k equal to 100, you kind of have the opposite problem, where you have probably less variance, okay, less variance, but high bias, okay, k equal to 100, high bias, less variance here. So k equal to 1, we have high variance. The classification boundary has weird enclaves and exclaves because of arbitrary points that ended up on the wrong side. With k equal to 100, we have high bias. The classification boundary doesn't do a good job of fitting the data because it's looking at basically too many neighboring points, okay? K equal to 10 is probably going to do the best job. And so you get kind of this boundary, and we can see it does a pretty good job of approximating the true relationship, which is shown in the purple dotted line. Okay, so something in between. Okay, let me, before we end, I just want to talk a little bit about tidy models. Tidy models is going to be the package or the framework of packages that we're going to use for modeling in machine learning, right? And so you're going to get that set up in RStudio by doing install.packages tidy models. And within tidy models, there are several packages. And so I want you to start going to the Tidy Models website and start familiarizing yourself with some of the different packages here. Okay, so if you click packages, they're kind of listed off here. Basically, the different parts that we're going to have. One is going to be our sample. This is going to be used for splitting our data, your original data, into a training set and a testing set, and also being able to do things like k-fold cross-validation or v-fold cross-validation. So for cross-validation as far as testing to see how well our models are performing. Okay. Another package is called Parsnip. Parsnip is kind of a framework that allows us to try out different models from different packages in R in kind of a unified format. Okay, so one of the great things about R is that there's a whole bunch of different packages out there that you can use for fitting different kinds of models. But that's also one of the drawbacks, is that each of these packages that get released have like a different syntax, have a different kind of form in how you would implement it. And so what Parsnip does, as these new packages get released, the authors of Tidy Models update Parsnip and basically include like little translation instructions. So you just have to learn how to use Parsnip. You can say, hey, I want to fit this kind of model, and I want to use this package, and Parsnip will automatically translate your instructions into the commands needed for that particular package, right? So you don't have to get bothered with all the different syntax of these different things. You can just learn Parsnip, and Parsnip will translate your things. And the authors of Tidy Models are really good about kind of updating, regularly updating Parsnip so that it can keep accommodating new packages that get kind of released. Okay, Recipes is a package that we use for feature engineering. Okay, so if you want to create dummy variables, or you want to kind of create cutoff points and things like that, you can use recipes for that. Okay, Workflows creates like a pipeline, and you do your pre-processing, your modeling, and it all kind of works through it. All right, and then we have Tune and Yardstick. Okay, Tune, as you do work with these different machine learning models, there's different hyperparameters that you can mess around with. So for example, with k nearest neighbors, do you want to pick k equal to 1, or k equal to 10, or k equal to 100? How do you pick that kind of parameter? That's going to be done with Tune, okay? And so basically allows you to kind of optimize, what setting do you want to use? K equal to 1, 10, 100, 50, something in between. You use Tune for that. And then how well is your model performing? You use Yardstick. Yardstick measures the performance of your model. Okay. And then you have Broom and Dials, and these are kind of like support packages. Broom allows you to, like, once you fit your model and do that, you can then kind of convert it into some kind of format that is easy to kind of work with. And then Dials is basically the different tools that are needed for tuning to kind of improve your different kind of hyperparameters there. Okay, so what I want you to do is to start reading the textbook on tidy modeling with R. All right, so be familiar with the tidyverse, and also I guess I'm under the assumption that you guys have taken 101A on linear regression, and so at least you have some familiarity with some of the basics there. And so this chapter 3 here in tidy modeling with R will kind of go over some of the a review of R modeling fundamentals, and then once we have that established, we can start getting into using tidy models for analysis there. Okay, there's some courses here. I've assigned Introduction to the Tidyverse as one of your homework assignments that you'll need to complete. I think it's also handy to go over some of these things as well. So you should have an invitation to Data Camp, and we have that. Okay, we'll wrap things up here, and we will see you. Or I'll have another video posted for the next lecture.